next up I want to talk a little bit about virtual memory. So if you remember, I enjoy drawing this virtual memory diagram. This time I'm just going to draw it in the editor. So we have our virtual address space that is going to be separate for each process. It's going to range from, I guess we'll talk about 64-bit systems, so it ranges from 2 to the 64 at the top, all the way down to down to 0 at the bottom. And then in the space, we've got a bunch of stuff. We've got our text section. We have our data section, and those are usually next to each other because those are loaded from the executable file on disk. And then we have some probably empty space. And then we at the top of memory have a stack. And then somewhere in the middle we have the heap. The heap grows up. And the stack is going to grow down. So this process here is going to be PID 20, and we're going to have we're going to say that each one of these things is a page. So this is going to be virtual page 2. This is going to be virtual page 3, skip 1, virtual page 4, virtual page 5. Sorry, skip 1, virtual page 6, so it looks like the diagram. They're not going to be that close together in practice. In fact, these regions are going to definitely be more than one 4K page, but just for the purpose of illustration, I'm giving them virtual page numbers. Now, each one of these virtual pages has to be allocated a physical page. So our physical page here is going to be 10, 11, 12, and 13. And there's no reason why physical pages are in any particular order, because we have a page table that allows virtual pages to be arbitrarily mapped to physical pages. Now, the other thing that we need to talk about our page table is for each one of these pages, we need to talk about flags. So our text section is going to be marked as read-only, because we don't modify code after the program is running, at least by default. And then the rest of these things are going to be mapped as private. Which means that they aren't shared between processes. Now, if we call fork, what's going to happen is we're going to make a complete copy of the page table in a new process. So we just called fork, and we have two processes now. And we're going to add some flags to both page tables. In fact, this operating system that I was being is inefficient. I can save some typing if, while I'm pretending to be an operating system, I add the flags before I copy the address space. But now we've forked, and all the stuff that was private before is now marked read-only, copy on write. And now as we go through and modify data, let's say we return first in, new process ID. Let's say we return first in process ID 21 and start writing stuff on the stack. We get a page fault because this is marked read-only. The kernel sees that it's marked copy on write. And so what we're going to do is we're going to go ahead and assign a new physical page here. Copy the data to the new physical page. And because now there's no longer any sharing between the processes, we can go ahead and in the other process mark that as not being read-only or copy on write either, because it's no longer shared. It's no longer shared as an optimization. Same thing will eventually happen with the heap. Let's say this is the first place we wrote to the heap. So now this gets to be physical page 15. And then the heap down here is flags private 2. And then maybe in neither of these processes do we ever actually write to the data section. And if we never actually write to the data section can be shared between the processes, even though it's marked private. So that's the quick review on the multi-process situation when we're doing fork and what virtual memory looks like. Now, we have another concept that we're going to be introducing today called threads, where this works a little bit differently. So in threads, before we get into threads, I wanted to talk about what happens if we do have shared data. So imagine for a moment that we had one more region here. So this is going to be virtual page. I guess it has to be 4, and the other one needs to be 5. This is going to be a physical page 18. So now what would happen if we had this shared page that we allocated with, or shared region that we allocated with mmap when we went ahead and called fork? And the answer is, if process ID 20 had this shared page before we called fork, then process ID 21 is going to have that shared page after we called fork, because it was in the parent address space, so it gets copied, that entry in the page table gets copied, and the flag says shared, so we don't have to do any of this read-only copy and write stuff to avoid having the two processes interfere with each other's memory. And so regardless of whether either of these processes write to that region of shared memory, the page table isn't going to change. It's already marked shared, it's already marked read-write, and so the physical page is going to remain shared between the two processes, and that's fine. Alright, so I wanted to introduce threads, and the reason I wanted to introduce threads is because it makes this picture a little bit different. So let's go ahead and take this process ID. Take this process. And so instead of calling fork, we don't need any shared data here. Instead of calling fork, the thing that we're going to do is we are going to call pthread create, which is the function that gives us another thread. We start with every process as one running thread. What a thread is sort of a thread is a running like chunk of code. It's the scheduling unit of the operating system. So when we have code running on a CPU on a modern system, the code that's running is the sort of state of that running code is represented as a thread. Processes can have more than one of them, but they always have to have at least one, because otherwise you wouldn't have any code running. Nothing would be scheduled in a processor. So when we call pthread create, what we get is we're going to allocate another stack. So this was the main stack for the main thread, and then we have an extra stack for the additional thread. That's going to have a virtual page that is different. It's going to have a physical page that is different, and it's still going to have the private flag. Now the trick here is that these two threads are now going to run concurrently within a single process, and so they're going to share all memory within the virtual address space. Here, in the process picture, figuring out whether we have data races, in the picture at least, is pretty straightforward. Data in the shared region is shared, so there's potentially a data race there. And data in all of these other regions is not shared, so we can't have a data race on it. In the thread situation, the data in these regions, all of the regions, is shared between the two threads. The threads can access that data if they can get a pointer to it. And therefore, all of the data in the entire process address space is potentially subject to data races. Now, we very carefully write our threaded programs so that we have control over which objects are shared. Usually, all that's actually shared is a few things on the heap, because those are the only things where we're sharing pointers between the two threads. But conceptually, any pointer could be to shared data. Normally, we do follow a convention where data on a thread stack tends not to be shared with other threads. It can get confusing if we take a pointer to our stack and give it to another thread, because that pointer could be invalidated because we returned from a function and things are happening concurrently, so it's going to be hard to understand what's going on. But that's just a convention, and it's not something that's universally followed. It's entirely possible to have one thread set a pointer to another thread to an item on the first thread's stack, and then even stack regions are shared objects. So that's what we're going to be talking about today. Threads. There's some advantages to having everything be shared by default. Realloc works nicely with threads, whereas implementing a version of realloc with mmap is kind of tricky, especially because these shared regions are set up before we fork, and so once we've forked, we can no longer really go modify the page table of the other process. We can only modify our own page table. There's ways to work around that, but if you're going to be sharing something like a vector, it's much more straightforward to do it with realloc and threads. Threads are a little bit more common as far as a solution if you really intend to execute things in parallel or really intend a single program to be concurrent, but I'll talk about that a little bit more later.